Thank you, Andrea, and thank you, Eduardo, for this nice invitation. So I'm Manibrata, and I'll be talking about pseudo-Dirac neutrinos and how can one use observations of neutrinos from a future galactic supernova, as well as the observations from 1987A that we already have, to put some of the tightest constraints on such scenarios of pseudo-Dirac neutrinos. So as with all these talks, let's start with a lightning quick introduction of the mechanism of a core collapse supernova. I don't need to go into too much details because Georg and Irina already covered the most basic aspects of it. So we're talking of massive stars, more than 8 solar masses, which at the end of hydrostatic burning would have an onion-like structure like this, with heavier elements as you go towards the center. And it finally ends with iron, because it's difficult to form energetically heavier elements than iron from hydrostatic burning. And now, as more and more of these elements start burning and collapse on top of the iron core starts growing in mass. And at some point, it cannot be supported by the electron degeneracy pressure inside the core. As a result, this entire system collapses. Now, as the collapse keeps on going, the central density starts increasing until it reaches nuclear densities, at which point there is again a resistance to the collapse. And this leads to a bounce, which leads to a shock wave. And we know that this shock wave is what leads to a successful explosion. What we still don't have a good idea about is that what energizes the shock wave. So what simulations show us is that as the shock wave goes outwards, it loses energy and eventually stalls. And our belief is that there are a lot of neutrinos emitted, which we know from simulations as well as otherwise, that the core emits a large number of neutrinos. And what we believe is that these neutrinos transfer their energy to the shock wave to cause a successful explosion. The crux of the story is that a large number of neutrinos are emitted. Almost 99% of the energy of the binding energy of the supernova is emitted in the form of neutrinos. So if we can capture these neutrinos, we'll not only know a lot about the physics that goes inside supernova, but we'll also understand the mechanism of neutrino flavor evolution inside such dense objects. So do we have a lot of experiments that we can look back upon to understand the flavor evolution of neutrinos? Well, unfortunately, we have not been super lucky. We have only had one galactic supernova from which we have measured neutrinos or detected neutrinos. This is the supernova 1987A, which took place a long time ago in the universe, but we only saw the neutrinos like around 30 years ago or so. And it happened in the Large Magellanic Cloud around 50 kiloparsec away. It was an 18 solar mass star, and many of you might have seen these images. And in terms of neutrinos, we have not detected a lot of them. Frankly, the detectors at that time were not really prepared to detect such a huge burst of neutrinos. And the ones that were operation which detected was the Kamiokande detector in Japan, the IMB detector in the United States, as well as the Baksan detector in Russia. And this is basically the handful of events that were seen. So what I'm showing on the left-hand side is a plot of the spectra, the number of events as a function of energy for Kamiokande, for IMB, and for Baksan. And as you can see, these are basically just a handful of events. The Kamiokande saw of the order of 10 to 15 events, IMB saw around 8 events, and Baksan saw less than 5. Even out of this, Baksan did not have a very clear, for Baksan, the backgrounds was not very clear, which is why some of these data are not, they're kind of contested. So they're not very clear whether one should include this in the analysis or not. So even if you exclude Baksan, the first thing that you see when you look at the data from these two experiments is that there is a slight tension between the data from IMB and from Kamiokande. While Kamiokande favors a spectra that is peaked at lower energies, IMB favors a spectra that is peaked at slightly higher energies. And one can try to do a more serious analysis of this by trying to fit this spectra. The way you would go about it is that you assume that the spectra from a supernova is roughly fitted by a pinched Fermi-Dirac spectra of this form, where this looks almost like a Fermi-Dirac with some alpha parameter, which basically gives you the pinching of the spectra. And essentially with this and with the total energy, which is basically the integrated luminosity and the average energy in the flavors, you try to fit the spectra. And this is what you get. So the Kamiokande spectra basically favors something like this, the black lines, with this being the best fit point. The IMB spectra, as you can see, favors something which has a higher average energy, but a lower luminosity, and this favors this. These two are, of course, slightly in tension, and the combined fit basically falls somewhere out here. Well, because the number of events is so low, the most obvious explanation would be that maybe this is just statistics, because we have so less number of events. This is just, if we have more events, maybe things would be better. But since we're theorists, we like to go for new possibilities for such kind of discrepancies. One might want to look at a more speculative explanation of this. One such explanation that I will like to discuss in this talk is that maybe what they saw was not just an effect of statistics, but an effect of the inherent nature of neutrinos. Maybe neutrinos are pseudo-Dirac, which is why you would see something like this. Now, I will explain what a pseudo-Dirac neutrino is. And the idea is this. You start with a generic neutrino mass matrix. This is what it looks like. You have the diagonal elements, which is what we typically call the Majorana mass elements, which are lepton number violating. You have the off-diagonal elements, which are the Dirac mass elements. Now, in this case, if you switch off the diagonal elements, you go to the Dirac limit where there is no lepton number violation. You basically have your active neutrino, you have a right-handed neutrino, and you only have an off-diagonal element connecting the two. Now, let's say you go to the opposite limit where you go to where basically these diagonal elements are much larger than the off-diagonal elements. Then basically you're in a scenario where there is an explicit lepton number violation. This is the Majorana limit where you have Majorana neutrinos. But then there exists a third limit where essentially the diagonal elements are non-zero, but they're much tinier as compared to the Dirac Dirac mass terms. This is what goes to this is basically a soft lepton number violation where these terms exist, but they're much smaller as compared to the other mass scales in the theory. And this is the pseudo-Dirac limit, where essentially the neutrinos are Majorana, but then for all practical purposes, they would behave as Dirac neutrinos. This is where the neutrinos would be known as pseudo-Dirac neutrinos. And what was shown in this classic paper was that if you work in this limit, you can take this entire 6x6 mass matrix and diagonalize this by an effective matrix that looks like this, where V basically is composed of two 3x3 block unitary matrices, where the first 3x3 is the standard unitary PMNS matrix that we all know of. And this is some other unitary matrix that works in the sterile sector. And then these are some phases which basically depends on the mass terms out here. Now, with this, if you use this matrix, what you would see is that in this limit of pseudo-Dirac neutrinos, your active neutrinos basically turn out to be just a maximally mixed combination of an active state and a sterile state. So you have an active mass eigenstate and a sterile mass eigenstate, and your active flavor neutrino is just a linear combination of these two in the most maximal mixture. What happens? So in this picture, what is the overall picture that you see? Because your active state basically splits into a linear combination of an active eigenstate, mass eigenstate and the sterile mass eigenstate. So your standard 3 neutrino picture now splits into this very interesting 6 neutrino picture, where each of these active mass eigenstates now basically splits into two components. So you, for example, for the nu3, you would have a nu3 active and a nu3 sterile, and similarly for nu2 and nu1. And these two would have a very tiny mass difference given by this delta m square, which is basically proportional to a product of these two factors. Now, of course, because we are in the limit where these mLs and mRs are much tinier, this delta m square is much, much smaller than the other conventional atmospheric delta m square and the solar delta m square that we all know. What this suggests is that along with the oscillations that we usually know and study about, the atmospheric mass square difference oscillations which exist between these two states and the solar oscillations which exist between these two states, one can also have oscillations that are driven by this very tiny delta m square, which basically happens between two of these mass eigenstates. So for each of these states, you can have a state that oscillates from an active to a sterile state with an oscillation frequency that basically depends on this very tiny delta m square. Now, of course, because this delta m square is super tiny, these oscillations will only take place at very large distances. And this can only be relevant for baselines, which would be super large, much larger than the Earth-based experiments that we consider. Of course, you can have the sun, you can have supernova, and so on. But for these cases, what one also must keep into mind is that there will also be an issue of wave packet separation decoherence. So essentially, we know that these neutrinos are massive, so they all can be described by a certain wave packet picture. And oscillations take place as long as the wave packets of the different mass eigenstates overlap. Now, at a time when these wave packets start separating, and they completely separate as they travel over long distances, these oscillations would start to cease. Now, because these neutrinos have masses, the wave packets would move with different velocities. And as a result, once they travel over long distances, the wave packets separate, and this reduces the oscillations. Now, one needs to take into account both these factors, oscillations over large distances, as well as the wave packet separation, to understand oscillations due to pseudo-Dirac neutrinos. And this is something that has been done also in previous papers. So people have used solar neutrinos to put bounds on these parameters. You can use the sun neutrinos from the sun to put constraints that go like this. So as you can see, these numbers are really tiny. So solar neutrinos can probe numbers like 10 to the minus 12 eV square. Atmospheric neutrinos are slightly less stringent, so they can probe numbers like this. Whereas one can model even the high energy neutrinos that come from gamma ray bursts and so on to probe numbers that go into this paradigms. So how do you calculate this probability? So as I said, you would have basically three kinds of oscillations. You would have oscillations driven by these delta m square atmospheric and solar, but they would basically get averaged out because neutrinos are coming from large distances. And mind you, right now we are looking at supernova 1987A, which happened at 50 kiloparsec. So oscillations due to these terms would be averaged out, but you would have oscillations due to this small delta m square. So essentially the probability of one flavored neutrino going into another flavor can be split into a product of two factors. One, the standard average PMNS matrix elements, and also one survival probability of the active neutrino, which essentially looks like this. Now, this expression is very similar to the standard oscillation probability that we have, excepting for this extra exponential damping factor, which comes because of this decoherence that I just talked about. So if you set this red term to 1, you basically have a term that goes like a sine square of the oscillation length, and then you get back your standard oscillation formula. But what this tells you is that if the neutrinos travel over a distance which is larger than the length over which they can maintain their coherence, this term would effectively average out to 0, and your flux would go down by a factor of 2. And this is what will be important in certain cases, as long as the distance traveled would be greater than the length of coherence. Now, what are the typical numbers that would happen in this case? So the oscillation length is basically given by a formula like this. It's inversely proportional to the delta m square. And for a typical ballpark energy of around 20-ish MeV and a delta m square, which is as tiny as 10 to the minus 19 eV square, these oscillations can take place over a distance of order 10 kiloparsec, which is exactly the ballpark value in which 1987A happened. And if you want to look at the expression for the coherence length basically depends on two factors. It depends on the delta m square, again, inversely. The more rapid the oscillations, the smaller would be the coherent length. And also it depends on the width of the wave packet, because as I said, the separation of the width of the wave packet is what leads to a decoherence in this case. So if you have a small wave packet, you would end up losing coherence faster. So for typical processes that create neutrinos inside a supernova, this number can be estimated through some order of magnitude arguments. And this comes out to be of the order of 10 to the minus 13 meter. And again, for a delta m square of order 10 to the minus 19 eV square or so, you see that the coherence length is greater than 100 kiloparsec. So if you're basically looking at galactic supernovas, the decoherence is not something that would become important. That becomes important if you look at something that comes from a longer distance, for example, the diffuse supernova background neutrinos. But then, because the oscillation length is relevant out here, you can have oscillations mediated by this very tiny delta m square. And this is something that we will see out here. So what we do in this plot basically is we take the supernova flux and we show two cases. One is this green case. So what we're plotting is a quantity which is E squared times this supernova 1987A flux with some best fit parameters. And we average them over a certain energy resolution function. And the green line basically shows the standard case that you would get. And in case you assume that the neutrinos are pseudo-Dirac, you see that there are these rapid oscillations that are driven because of this tiny delta m square. And these rapid oscillations can be something that would be relevant for explaining this discrepancy between the IMB and the Kamiokande data. How so? So I'm just showing you one tentative example out here. We can go into more details later on. The idea is this: once you let these oscillations, you can basically get, instead of the green line, which is the standard fit to this data, you can get this magenta line. And as you can see, this does provide a marginally better fit because, for example, in this bin, Kamiokande sees no data, and this would let you, this actually allows you to get a dip in this data if you tune your parameters in a way that you would, if you tune your delta m square in a way that you would get an oscillation minima out here. Or for example, you can get an excess of events in this bin where IMB does see an excess of events and the spectra actually goes down from the best fit. So doing these kind of analysis would allow you to give you a better fit to the data from 1987A. And this is exactly what we find out here. So what I show out here is basically a log likelihood analysis. We do an unbinned log likelihood analysis to the data for Kamiokande and IMB and Baksan individually as well as a combined data. And we try to ask the question as to whether the data favors the pseudo-Dirac hypothesis or not. So on the x-axis, we plot the delta m square in units of EV square. And basically, when you go to very tiny values of delta m square, you go to the limit where there are no oscillations. So the neutrinos again fall back into this usual Dirac limit, because in this limit, the delta m square is so tiny that the length of oscillations is larger than the length of the observable universe. So for all practical purposes, they're not oscillating through this delta m square. Now, as you let this delta m square vary, you would have these oscillations take place. And then you ask at what point of delta m square is your data being fitted in the best possible way. And this is what we get. So let's look at these lines individually. So the blue line basically shows you the Kamiokande data. And as you can see, compared to the no oscillation hypothesis, the Kamiokande data is marginally favored by a delta chi-square of order 1 or so. On the other hand, the IMB data, for example, is again marginally favored by a delta chi-square of slightly closer to 2. But then the nice thing is that all of these converge into a delta m square, which is roughly around some value times 10 to the minus 20 EV square. And this is where you get the best fit scenario. And even for Baksan, you get a slightly shifted value, but it's still better than the no oscillation hypothesis. Again, remember the Baksan data is actually plagued with a lot of background. So this doesn't have as much importance as the other two data. But then what you can do is you can do a combined fit of all the data, and then you get this solid magenta line. And as you can see out here, you get a clear preference for a non-zero delta m square with a delta chi-square of the order of 3 or so. Of course, this in terms of a statistical analysis doesn't carry a lot of weight because it's a very tiny number. But then again, we're dealing with a lot of small data. And what we find very intriguingly is that in order to fit the data of these two combined experiments, it helps to have a pseudo-Dirac nature for the neutrinos with a non-zero delta m square, simply because you would want to, the data would prefer something that explains this dip at this bin and explains this excess of events in this bin. And if you want to combine the two, you would get a non-zero delta m square to be favored over a no oscillation hypothesis. Furthermore, if you want to turn this question around and ask that I have this data, and if I want to use this data, can I exclude a value of delta m square that has not been probed before? You see that this combined analysis actually rules out a certain chunk of region of delta m square with a delta chi-square that is greater than 9. That's almost like a 3 sigma effect if you would want to do a Monte Carlo analysis and then assign some confidence limit to this. So what it does is it allows you to exclude a value of delta m square in this region, which is some number times 10 to the minus 20 EV square with a delta chi-square greater than 9. And if you remember the values that I was showing you from the solar neutrino analysis as well as the other ones, this till now would be the smallest value of delta m square that one can constrain with data that we already have from Supernova 1987A. And then with this, we can also do something like what I showed before. We can try to see that with this new hypothesis, what kind of region in the total luminosity and the average energy plane would the data favor. And this is what is shown by these colored contours. And in dashed line, I show you the previous results that was assumed that we got by assuming that the neutrinos are just Dirac and not pseudo-Dirac, and they are roughly compatible. But then, as in this case, in the pseudo-Dirac case, the data prefers a slightly larger value of the total luminosity, which is this one. But apart from that, within 3 sigma, within a delta chi-square of 9, these contours are roughly compatible. What this allows us to do is it allows us to ask the question that, let's say, okay, we have got 1987 and we had 30 events and so on, but then now we are much better prepared. And in case of a next galactic supernova happening within a distance of 10 kiloparsec or so, we would have thousands of events. And can upcoming experiments do better than what we already have done with 1987A? And indeed we can. We have plans of having Hyper-K and Dune start up and running by the next decade. And these are massive experiments with a lot of effort aimed at detecting supernova neutrinos. And what we studied was and found out was that in such a hypothesis, Hyper-K and Dune can actually confirm or rule this scenario out with a high confidence. So for example, this green contour is what Hyper-K would basically probe. And Hyper-K can in principle probe region delta m square as tiny as 10 to the minus 20 EV square for all possible values of this wavelength, this wave packet width parameter that you can think of. Of course, this parameter is a free parameter in our model because this in turn has a lot of uncertainties associated with it, which is why we allowed it to run. But for all possible values, it can probe delta m square as tiny as 10 to the minus 20 EV square. If you let this wave packet width to go to even smaller values, which probably would be slightly more towards the unphysical side, you would still be sensitive to smaller delta m square, because once it goes to smaller values, a wave packet decoherence starts coming in, and then basically your number of events start going down. So you can fit it with an even smaller value of delta m squared. And for example, Dune, which is a slightly smaller detector, would also be sensitive to larger regions out here. And this is what you can, this basically this darkish band is what Dune would be sensitive to. On top of this, we also show what Supernova 1987A already ruled out. So in the same plane, Supernova 1987A basically ruled out this this blue region. And as you can see, upcoming detectors would have a much higher reach as compared to these regions. One interesting thing that we didn't work out in this paper, but something that would be relevant would be the role of non-electron neutrino detectors in this case, as Irene slightly hinted in her talk, that once one starts detecting these non-electron flavor neutrinos, they would also basically undergo such oscillations that we discuss in this talk. And these oscillations would actually can be easily probed by detectors which would be sensitive to these kind of non-electron neutrinos. So they are going to play a very important role in constraining this kind of a hypothesis from a future galactic supernova. So this brings me to the summary of the talk. I think I'm already over time, but basically what I wanted to emphasize in this talk is that core collapse supernovae are sensitive to a very tiny value of delta m square, which is not otherwise accessible to any other experiments currently that are running on. And to emphasize that point, I show in this plot basically in the landscape of the energy of the neutrino and the baseline of the experiments, what values of delta m square a core collapse supernova can probe. So for example, these dashed lines, the slanted dashed lines, show logarithm values of the delta m square that different experiments can probe. So for example, accelerator and atmospheric experiments can probe these values of delta m square 3.1 and 2.1. You have the sun that can probe a delta m square of much tinier value for this pseudo-Dirac neutrinos. And then you have the DSNB, which in principle, if we can detect, can also go to much smaller values. And our currently supernova, the 1987A basically lies in this green region. So we can already probe a delta m square of 10 to the minus 19 eV square. Now, once one has a detection of the DSNB, one can go to even smaller values simply because the neutrinos are coming from a much longer baseline to almost 100 kiloparsec or so. But what is important is that once we use the data from 1987A, we can already probe a delta m square as tiny as 10 to the minus 20 eV square. And this is till now the smallest value of delta m square that has been probed as of now. And once one goes to a future core collapse supernova, it can be used to probe even smaller values depending on where it happens and how many number of events we have. And with this, I will conclude this talk. Thank you very much.
Okay, so thanks a lot for the very nice talk and to be on time actually, so don't worry. Any question for the audience, from the audience? Let's see. Eduardo raised his hand. Okay, yeah, because he cannot raise it. Okay, Eduardo, go ahead.
Yes. So I have a question. Like, is there any reason why you expect this delta m square to be this small, or it's just like? And that's the first question. The second question is: I see that there is a very large range of masses of delta m square that is not currently explored, and I was wondering if you considered any other way of constraining other delta m squared.
Right. So the thing is, we want to explore limits where neutrinos are pseudo-Dirac, and that limit specifically works in the case where this Majorana mass terms are extremely tiny, because only in this limit can you go to this. Can you theoretically go to this approximation and write it as a linear combination of this? In the intermediate range, it's not so easy to do this because certain approximations go into this that doesn't work. So you can always do the more general thing, but this wouldn't work. And to answer your second question, what essentially the only way to probe this is by looking at these oscillations over long baselines. And as you said, in these regions, it's very difficult to have an object that would be accessible at these long baselines and then produce neutrinos at this energy, because the high energy neutrinos that we get are all lying out here. If you want to probe something out here, we would need a star like the sun that would be out here producing a neutrino that's much higher energy. So I don't know of any objects from which I can probe these neutrinos, at least from this plot. But yeah, I mean, it would be interesting to know if something like this exists or not.
Can I ask actually on something on the first question of Eduardo, because I was also wondering, and sorry, Rena, I didn't see you. I will give you the word too after that. But So under the model building point of view, is that easy not to screw up this smallness, in the sense that I imagine that, as you said, you will need a huge hierarchy between the Majorana mass and the Dirac mass, right? So it will be like mass, like lambda v, right, with your vev, whatever. So I was just wondering if this, probably yes, but is this hierarchy stable, for example, if you consider higher dimensional operators? Because it's a huge hierarchy, right? And are there studies in that direction?
So I don't know of models apart from the usual ones. The usual ones, what they do is they consider this usual Weinberg operator, and then they go to this limit where this comes from any kind of effective theory that would give rise to the Weinberg operator. But I don't know of any such work that actually tries to build a more concrete model from a higher energy perspective giving rise to these operators. But I think as long as you consider these operators, this should be stable under radiative corrections, because there will always be some symmetries that is going to protect this term from blowing
like
up.
some lepton number.
Exactly, yes.
Yeah.
And the only thing that you want is that these oscillations be driven by a very tiny delta m square, because then effectively for all terrestrial experiments, your neutrino acts like a Dirac neutrino. So even for like things like BBN and so on, your neutrino is just a Dirac neutrino. It only starts acting like these sterile components only start showing up once these oscillations take place over long baselines.
Okay, good. So now, Irene, please go ahead.
Yeah, thanks, Manibrata. I only had a small curiosity. So have you, for the future prospects, did you also look at how the neutrino curve would change? Like whether these oscillations then are leading to some, I don't know, funny features in the temporal evolution of the signal?
Oh, no. We haven't looked into that yet. No, this is something that we did discuss at some point, but we haven't looked into that, because this would also lead to some funny evolutions in the temporal signals, because the flux hierarchy would change and this oscillation feature would also come into this. But for this entire analysis, we were only focusing on a time integrated signal. But yes, that would also be relevant in this case.
Okay, thank you.
Okay, fantastic. So I don't see other other questions. So we thank again Manibrata, and thanks a lot. And now